I welcome you again to this course of NPTEL on earthquake resistant design of foundations, and this is the 7th lecture in the series, and we are continuing with the second module, that is on the shallow foundations. Shallow foundations, when we talk about, we already covered general requirements, bearing capacity settlement, combined footings. Continue with that. Today we are going to talk about Raft foundations, and let me tell you about the background. When you have found out that the spread footing and isolated footing is not enough, then as discussed in the last 2 lectures, that we should go for the combined footings, where you combine the footings of 2 isolated columns together, or you use strap beam, strap footing. So, but if it is come out that that combined footing is also not enough, particularly for earthquake loads where the settlements are large, then we go for the raft foundations. So, though Raft is also Raft foundation, or what we call the mat foundation, that is also under the category of shallow foundations, and we are going to talk about that today, and these are the points which we are going to consider today. Let us introduction about the Raft, then what are the design concepts, the criterias, and then there is code IS 2950 part 1. So, the codal provisions given in that he is also going to discuss. In the code, that there are many issues, other issues are from the code itself, but they require discussion, they require that clarification how to use it, that code, and the lot of things are given in the code IS 2950 for Raft foundation, particularly related to its design. So, we are going to cover about that. For example, determination of Young's modulus ES, subgrade reaction K, they are given in the code, rigidity of superstructure foundations, all the codal provisions will be covered, and then finally we are going to discuss the numerical problems. So, we are going to talk about some part today, and next in the next lecture continue with that. So, continue with this today. When we talk about a raft foundation, mat or raft is like a combined footing which we have discussed earlier, but the difference is here. In the combined footing you have 2 columns under the footing, but here number of columns are very large, and that covers the entire area beneath a structure, and it supports all the walls and columns. So, if you are going to put the footing, combined footings on under the more than 2 columns and particularly multiple columns or walls, then you require what is called raft or mat foundation. What are the requirements and what are the uses of the raft foundations? When the allowable soil pressure is low and the building loads are heavy, then it is recommended, even without the earthquake, that one should go for the raft or mat foundation. And because in this case the use of spread footings would cover more than 50% of their area, and it will not be economical to use the spread footing, rather it will be more economical to use mat or raft foundations. So, the first condition is that if the soil pressure is low, the means the quality of the soil is not good, and the loads coming from the superstructures are heavy. In that case, it is recommended that one should go for the raft foundation, and the reason being that it will help in having the settlements within the permissible limit. Then the second case, you know that we can allow more total settlement, but the differential settlement is always less than the total settlement, and if differential settlements is difficult to control, when soil is highly compressible and erratic, in that case, in the second case also you can go for the raft, and it may help you to decrease or reduce the differential settlement. And further, the raft foundation or mat foundation will help in reducing total settlements, particularly above highly compressible soils, by making the weight of the structure and raft equal to the weight of the soil excavated. Many times what is a term, it is we call floating foundation. In that case, what do? You excavate the soil, and after excavation you know that you put your footing and the structure. So, if the weight of the excavation is same as the weight of the superstructure and footing, that means there is no change in the stress at that point, and then even if your soil is very weak, still it will be able to carry all the loads and of the structure, superstructure. Continue with that. So, after this let us talk about the design concept in broad sense, and then we will talk about, when we discuss about design, we will discuss in detail about that one. Normally rafts are designed as reinforced concrete flat slabs. So, the foundations are similar, though it looks when we go you to go and see the construction of the raft foundation, then you will find that they are similar to casted like a slab which is like on the top of the room. If you see this the slab on the on this room, so the design is similar to that one, and though it is foundation, it is not the the ceiling. If the center of gravity of loads coincide with the centroid of the raft, in that case the upward load which is coming from the soil can be regarded as uniform pressure, and this uniform pressure can be considered total downward load, which is the load coming from the superstructure plus divided by the area of the raft. However, the weight of the raft is not considered in the structural design, because the raft is directly supported on the soil and its load is directly carried by the soil. So, the raft of weight of the raft may not be required to consider. Usually reinforcement in rafts are kept heavier than required by the analysis, and the reason is simply because the analysis which you carried out neglects the moment and shear caused by the differential settlements. So, it is conventional that the raft foundations are heavily reinforced than what you find reinforcement obtained from the from the calculation part. Continue with the design concept. What is done? The raft is divided into a series of continuous beams or strips which is centered on the appropriate column rows which is given in the code. With the raft, a series of beams, the shear and moment diagrams may be established and the mat can be designed. What we do? We have a series of beams, primary beams and then secondary beams, then we find the shear force diagram and bending moment diagram, and once you know the shear force bending moment diagram, then we can design the footing. However, this type of concept, this lead to a conservative design, and which is for the simple case always it is we go for the conservative side. The raft may also be designed in some cases as an inverted flat slab using heavy beams from column to column. In case of inverted flat slabs, what you do? The load of the slab is, rather than transferring on the columns, it is transferred through inverted columns and then finally through the walls and other things. In the same way, the raft can also be designed. The portion between the beam is then designed as a conventional one way or two way slabs. Then if there is a difference when you design the raft foundation on clay soil and the sand, in case of raft on the clay generally fails in shear, while the danger of shear failure on sands is very remote and the settlement criteria governs the design. So, when you design the raft foundation for clay soil, your shear criteria will govern the design, but when you design the same thing for sandy soil, then settlement criteria governs the design. So, with this let us talk about the settlements in rafts. The settlement is a major issue for which rafts are popular. That means the settlement, because this primary objective of the raft is to decrease or reduce the differential settlements. So, this a raft may undergo large settlement without causing harmful differential settlement. So, that means there is a difference when you go for the raft foundation between total and differential settlement compared to other types of foundation like spread footing or combined footing. That means the differential settlement is a fraction of total settlement. For example, for spread and isolated footing, normally differential settlement may go as high as 75% of total settlement, but for a maximum settlement of 50 mm total settlement in the raft foundation, you will get a differential settlement up to 20 mm only. That means it is 40% of the total settlement only. So, that means total differential settlement is not large in case of raft foundation. So, as a result, even if you increase the total settlement in the raft footing, which may be even higher than the isolated footing or spread footing, still differential settlement is lower than the what you have isolated footing or combined footing, and the raft foundations are known for it. That is that the basic concept comes from that. If you want to avoid the differential settlement, you do not find any solution in the foundation, go for raft foundation and it will solve the problem if it is structurally like it is able to carry the loads. Now, when we talk about IS, this is this I think this code which you have seen, this code was here IS 2 sorry, this was okay. So, the IS that code number was like this was IS 2950, yeah, this is the code here. So, somehow this one, okay, then let me correct this one, this is 0 somehow IS 2950 part 1 1981, and this is code of practice for design and construction of raft foundations, that is part 1 design. So, this is the code on the raft, and this suggests that maximum settlement should be limited for raft on clay, it could go up to 65 to 100 mm. So, 65 mm, it is not in the minimum, though of course minimum value can be less, but normally it can be in this range. Then raft on sand, the range is 40 to 65 mm, but even if you have less than 40 mm there is no problem, as you know that as if as a, so but that means in case of clay, if you are using raft, then you can go as high as 100 mm total settlement, for the sand for 65 mm settlement is allowed. Now, continue with that, what are the given in the code, this code which we have the like that is a code of practice for design and construction of raft foundation in the part first. So, let us discuss the salient features of the code. When we talk about this, one of the important issue in the design of raft foundation is calculation of what is called modulus of elasticity ES, and you know the modulus of elasticity, Young's modulus, that it is not easy to find in the lab, you require the special type of test and other things. So, one way that you can conduct some test and in the laboratory test and get the value of ES, and then that Young's modulus may not be even applicable in the field. So, what this code suggests, that you can find this value of Young's modulus using plate load test, and plate load test should be conducted as per the code IS 188 1982, and that is for the sandy soil. In that case, the Young's modulus for the plate load test is given by the relation which is written here, this is given in the code. Let me explain what is here. In this case, Q is intensity of contact pressure, and that is itself is a question how to find, and we will discuss that later, that how to find this intensity of contact pressure. Then B is called least lateral dimension of test plate, which is known as settlement, it is measured in the plate load test. Poisson's ratio, mu is the Poisson's ratio, and IW is influence factor, which is normally taken 0.82 for a square plate. As we discussed the plate load test, if you recall that in the when we discussed the shallow foundation, I think it was on the fourth lecture, and at that time you know that for plate load test you use a square plate with the size of 30 centimeter to 75 centimeter, okay, and for this plate this influence factor is as recommended by code maybe 0.82. So, only the thing is in this case is the value of Q, intensity of contact pressure. If that is known, then you can find the Young's modulus using this empirical relation, and this empirical relation is coming, the data in this empirical relation is still required from the plate load test, like for the example settlement and the dimension of the plate is required. So, but plate load test is easy test and which is easily available, easily can be conducted and find out. Okay. Now, continue with that, then how this determination of ES, in case of this ES you have find out from the plate load test, and then there is a effect of the size of the raft, because you have the size of the plate and the size of the raft is different. So, the code says that effect of size of raft can be taken care by this equation, where ES is for the raft and EP is for the plate, Young's modulus, and BP and BF are nothing but the width of foundation footing as well as plate, and so using this equation you can find the Young's modulus applicable for the footing. In earlier this will be actually giving you the value of EP. So, this will give this relation will give the value of EP, and then you can put in this relation and get the value of ES. Then ES can also be, this was the case when you conducting the plate load test. Suppose if you have the data from CPT, the CPT stands for the cone penetration test, and cone penetration test, and we discuss little bit about cone penetration test also when we talk about shallow foundation, and if you recall that the bearing settlement using CPT was also discussed in the last lecture. So, for the CPT data, ES can be found out 2 times of CKD, where CKD is cone resistance and this is simple relation, but plate load test will be more appropriate and you know that more reliable for this. So, this if you do have the laboratory test data, for example cyclic triaxial or resonant column which can give you the Young's modulus of the soil directly, then this can be find out, or otherwise if you know the shear modulus, then you can use the where mu in this relation is, you may be aware that this is used for Poisson's ratio. Okay, this is so this is so this was that how to determine the Young's modulus ES using this one. Continue with that. If you see the this code IS 2950 part 1, then there is a, because with the Raft foundation one term is very important which is normally used, that is modulus of subgradation K, because the design of the Raft footing later on which we are going to discuss is based on modulus of subgradation K. So, it is important that you ascertain this value of the modulus of subgradation, and as usual if you can get this value of K using some appropriate test in the whether in the field or in the lab, that is better. But if it is not possible to conduct the test, that in that case the code suggests that you can take the values given in this table, and naturally these values should be used only when you are not able to conduct the test or otherwise. So, what this says, this code says, if soil characteristics are for this RD stand for the relative density. So, this is relative density, you know the RD in short, relative density, and when we talk about this term relative density, you may be aware that this term is more important for the sandy soil rather than or cohesionless soil rather than clay. So, this RD is categorized in 3 categories. You have loose, medium and dense sand. Based on the SPT n values, if SPT n value is less than 10, then we categorize loose, if it is between 10 to 30 then medium, and if it is more than 30 then dense sand. Corresponding value of K is given here in kilograms force per centimeter cube for 2 cases. If you have soil condition in dry or moist state, then the value is listed here for submerged state. So, that means for dry and moist state 1.5 kilogram force per centimeter cube. So, naturally this data, this code is given in kilogram force per centimeter cube, and suppose you want to calculate in the SI values, then you need to have this value. Kilogram force, you may be aware 1 kilogram force is nothing but 10 Newton, okay, and centimeter cube is 10 to power minus 6 meter cube. So, this comes out to be 10 to power 7 Newton per meter cube, that means you have 10 mega Newton per meter cube, that is like this value comes out to be. So, this is the conversion you can use that is there. So, that is fine. So, while using this table, what I want to point out that the values are given in kilogram force per centimeter cube, not in kilonewton. So, or this one. So, this may be 10 to power 4 or other, which is more popular unit, kilonewton per meter cube. So, this way you can find this 10. So, this was the case, and for the cohesionless soils, and you see for the cohesionless soils, naturally you have the higher values in dry and moist state. When you talk about submerged state, the values decrease from 1.5 to 0.9, 1.5 to this range, this is the range. So, depending on that you can use the interpolation, this value is between 10 to 30, 1.5 to 4.7, and if it is more than 30 then 4.7 to 18 depending on the value of n. If you have the n equal to 30, you can go for 4.7, and then for higher value you can use up to 18, and for submerged state instead of 1.5 it is 0.9, that is about 60% of that, and here also instead of like. So, for submerged state the values are about 60% of for the dry and moist state. This was the case when you have the cohesionless soils, but when you have cohesive soils, that means clay, in that case consistency is more important than you have SPT n values or relative density, because therefore the clay, that the term will be more applicable. So, if you have steep clay, then UCS here you may be aware that unconfined compressive strength, unconfined compressive strength. And this can be found, UCS can be found using lab test, because this will you will require a laboratory test for to get this value. You collect the sample from the field and test in the laboratory and find the value of UCS. So, if UCS is between 1 to 2, that is stiff clay, then K can be 2.7 kilogram force per centimeter cube. If you have very stiff, that means UCS between 2 to 4, then 2.7 to 5.4. If it is hard, that means 4 or above, then the value of K can be 5.4 to 10.8. So, the modulus of subgrade reaction can be determined using the data given in the code if you are not able to conduct the test. Continue with that. Now, if you see in the code, though code you can read, but what is my task is to explain the things, salient features, and let me emphasize on this, that raft footing is play a very important role in case of earthquake. So, that is why we are discussing here. So, let us talk about design consideration. So, then for design considerations, choice of raft type, this is given in the next slide. So, and that is given in the code also. So, you have different types of the pedestals, and then using that different in different conditions, different types of raft foundations are used without pedestal, with pedestals, and all these things are there as given in the next slide. Then you have the allowable bearing pressure. Then allowable bearing pressure shall be determined in accordance with IS 6403 1981, and if you recall, we have discussed this code already in shallow foundation, IS 6403 1981, and the soil pressures come from two criteria. First criteria, that dynamic there should be bearing capacity criteria, where you apply a factor of safety of 2.5 or 3. In that bearing capacity criteria, you have an equation for QU, ultimate load, like that QU, and then QU gives ultimately after applying factor of safety QS, self bearing capacity. And the second criteria is from the settlement. So, without exceeding the self bearing capacity of the soil and settlement, you determine what is called the allowable bearing pressure. So, what is allowable bearing pressure? We have already discussed. Then the depth of foundation, it is generally said that for the raft footing it should not be less than 1 meter df, and df, what is df is defined, df for any footing is defined the depth from ground level to the base of the footing, not at the top of the footing. That is the important thing to understand, that is it is up to the base of the footing. So, it should be not be less than 1 meter. If you recall that for minimum loads, I mentioned that when you go for a spread or isolated footing, the minimum depth of foundation is 0.5 meter. Even if you are going to make a boundary wall or that very small not heavy loads are not there, still the depth of foundation required is 0.5 meter. But the same for the raft footing, it is recommended that it should be at least 1 meter. Then when we talk about subsoil water pressure, the uplift due to the subsoil water shall be considered in the design. So, these things, these topics has been further given in the code in detail. So, if you come across that, then you can go, but these for explanation. Now, when we go for the design part or before design of the raft foundation, it is important that you understand what are the methods of analysis. And in the code there are two methods of analysis are given, and these methods of analysis will help you the determination of the distribution of contact pressure Q, as if you recall in the last equation when you need to find the value of ES, a factor Q was coming, and determination Q of Q itself is a problem in the raft footing, and how to find the value of Q, we are going to discuss that now. For that discussion, the code says that methods of analysis for raft foundation, there are two types of analysis. One is assuming that raft is a ridged foundation, and that is called conventional method, and naturally that is easier once we have assumed, and this is on conservative side, and this is based on the assumptions of linear distribution of contact pressure. So, E is missing in this case, contact pressure. Okay. And another way another method is called flexible foundation, where it is assumed that the subgrade consists of an infinite array of individual elastic springs. That means the second method, in the second method you assume that your soil will act like a linear springs, and your footing, raft footing is situated on the soil. So, soil will be modeled as an array of infinite linear springs. Okay. and in the first method. So, first method is simple, conventional. Today we are going to talk about the first method, and in the next lecture we are going to talk about the second method, that is flexible foundation. So, let us talk about the rigid foundations, what are the assumptions, how it is carried out, and what is in the conventional method. So, in the conventional methods, that is for rigid foundation, this is based on the assumptions of linear distribution of contact pressure. So, first assumption, it is assumed that contact pressure is linearly distributed, that means below the raft the contact pressure which is coming from the soil, it will be linear. It is not uniform, there is a difference between uniform and linear, we have discussed yesterday in the combined footing. If you recall, when you have for rectangular footing, it was uniform pressure distribution, but for the trapezoidal footing it was linear. So, anyway, the linear means it is linearly varying then, and the basic assumption of this method, the foundation is rigid relative to the supporting soil. That means, the Young's modulus of the foundation is quite higher compared to the shear modulus or Young's modulus of the soil. So, if your foundation is made of concrete, reinforced concrete, so in that case this assumption is very valid, because there is a large difference between the strength of the concrete and the strength of the soil. So, this assumption will be valid, and the compressible soil layer is relatively shallow, that means you do not have this and then your soil should also be little bit good quality, it should not be very bad quality for using this method. Then the contact pressure distribution variation is assumed as a planar, such that the centroid of the contact pressure coincides with the line of action of the resultant force of all loads acting on the foundation. So, this is important. I think if you recall, the same assumptions we have done for rectangular combined footing, where what did we do, that whatever loads coming from the top, so resultant of that load should pass through the centroid of the footing, or you need to design your footing in such a way that center of gravity of the footing is same as the line of action of the resultant force, and in that case the linear, you will find there is a linear distribution of contact pressure. So, that is this part. Now, how we can achieve these are the assumptions which is on this method. So, there are conditions, if those conditions are satisfied, then we can use this method and we can go ahead. So, what are the conditions in which this method can be applicable? This method, which is called this rigid foundation or conventional method, this method may be used either of the following conditions. You need to understand, when either of the following conditions are satisfied, that means out of A and B, if any one of the conditions is satisfied, then you can go for this method. It is not necessary that both conditions need to be satisfied. The first condition says the structure behave as a rigid due to the combined action of the superstructure and the foundation, with a relative stiffness factor K should be greater than 0.5. If value of relative stiffness factor K is more than 0.5, then we can use this method. Now, what is K and how this K can be determined is given in appendix C, and we will discuss that appendix C. The second condition, the column spacing is less than 1.75, this is 1.75 not dash. So, 1.75 divided by lambda, and this what is lambda we will discuss when we talk about appendix C. So, if either of these two conditions are met out, then you can use this conventional method or rigid foundation method. Now, continue with that. There is an article also that this continue for this method. In case of uniform conditions, when the variation in adjacent column loads and column spacings do not exceed 20% of the higher value, the raft may be divided into perpendicular strips of width equal to the distance between mid spans, and each strip may be analyzed as independent beam with known column loads and known contact pressure. See that when you have a number of beams, then there will be coupling between those beams, and it will be difficult to design. So, if you simplify the problem can be more simplified if this condition is met out. That means, if when the variation in adjacent column loads and spacing do not exceed 20%. So, whatever maximum value, you pick up the maximum value, and the difference should not be more than 20% in any case, then we can go for this method, and this can be analyzed as independent beam with known column loads and known contact pressures. Now, appendix C, let us talk about appendix C and then we will get over with this today's lecture. As you recall, in that ultimate aim is to find the value of k and lambda, which are coming in method of what we call the rigid foundation. So, the rigidity of superstructure and foundation can be defined as EI from this relation, and this looks long equation. So, we will discuss how to use this one. So, you have this the terms here, the this notations are given in the code also and explained in this foundation raft. So, you have here this is kind of a pylon, you have this the distance between this foundation raft is here. So, you have the difference, HU is given length of upper column, HL length of lower column. So, you have the on the top of the this is ground level, this raft is here. So, this is basically elevation, and B is the that is the distance which is also discussed here. Okay. So, this high B was the distance there between this one end to another end for this in longitudinal direction. So, HU and HL are already given in the figure. L is spacing of the column, which is also given here this in this direction, and IF is moment of inertia of raft, which is mentioned here. So, in this case now you know the value of HU, HL, I and IF, and then using this you can calculate other things. For example, prime values IB prime, IL prime, IF prime, these if these data are known, then you can calculate. Once this is calculated, then you put on the top equation and then get the value of EI, where E the EI will be this rigidity of superstructure and foundation relative rigidity, and if EI is known from this equation, then what you can do, then you can have the relative stiffness factor K, whether a structure behaves rigid or flexible depends on the relative stiffness of the structure and the foundation of the soil. So, the K values, what is K? K will define between superstructure versus your foundation. So, if you see for whole structure, K is a ratio of EI versus ESB cube into A. What you have here, EI we have already got this relative rigidity in the last slide, and ES is the Young's modulus of soil, that also we have found in using the appendix A of the code. B is the distance mark already, and A is perpendicular distance and B is bending axis. So, as written here, A is in perpendicular direction and B is along the bending axis. So, A and B cube are the dimensions. So, as a result what you will have, if you see this, recall this equation. So, I and B cube and A will have the same dimensions. So, this whole structure K will be that K will be a dimensionless factor. So, relative stiffness factor is a dimensionless, this is no dimension. So, you need to understand that K is dimensionless, there is no dimension, ratio only, dimensionless. For the if you have the whole structure, this K which is A for the rectangular raft or beam, it can be simplified as given here, where E and ES is the same as earlier, where E will be the Young's modulus for the concrete and ES is the Young's modulus for the soil, or you can say E is the Young's modulus for the raft foundation and ES is for the soil, and D by B cube, where if D B is the same as in the dimension in the bending axis, D could be either the dimensions in other case. So, using this ratio you can find the value of K. For circular rafts, if you have the circular rafts where R is the radius of the circular rafts, then this can be found using these relations given here. And once the K is known, then lambda factor which was also coming can be determined from this relation, where EC is the Young's modulus of concrete, I is the moment of inertia, K is used from this equation, K is same as coming this one. So, this K is kept, if you use the capital somehow, this is I think this should better, you should stick this is all right. So, I would say that it should be small k here, sorry about that, and this should be smaller k and this should be all right. So, normally this is smaller k for relative stiffness factor. So, once you have this k be for ECI 1 by 4, so using this relation you can find the value of lambda. Once lambda is known, k is known, then what you can let me go back. So, then you can check whether condition A is satisfied or B is satisfied. If none of these conditions are satisfied, then we cannot use this method. If one of the condition is satisfied, then we can go for this method using this ridge foundation. And in this case, for this method, principle is very simple, that you need to make sure that the analysis is done in such a way that total loads coming from the superstructure, they are passing through the center of gravity of the footing. That is the basic concept of this method, that is ridge foundation. In the next lecture, we are going to talk about flexible foundation, that is 5.2, and we will continue with that. So, thank you very much for your kind attention, and we will discuss, continue with that. Thanks.